okay.
Very good. Okay. So it's an honor to give the first lectures for the summer school on electronic structure calculations. I'm really impressed at how many people are there. It's also an honor to be associated with Young Hoon Kim, who is my student, as has been stated, and I just want to say that it's wonderful to see how much that you've done since you finished as a student, and it's a joy also to see people that I know like Jae-Jun Yu and Ho Lee and Young Kwan, and I must say that it's definitely a pleasure to see these great scientists I've worked with in the past. So the title of my lectures is Electronic Structure, because I want to put it in the big picture. The first lecture has a lot to do with density functional theory, but I want to start with putting things in perspective in the big picture. That electronic structure is a many-body interacting electron problem, one of the grand challenges of physics, or maybe I should say it's many of the grand challenges of physics, and it contains deep fundamental issues and exciting new discoveries happening every year. It also has important applications with consequences for all areas of science and technology, and so it must be quantitatively quite accurate to actually do something that helps in understanding real materials and real processes. But how can we possibly understand and calculate properties accurately for such a hard problem? The major breakthrough was density functional theory, and it's what's made possible the quantitative calculations that have revolutionized the field. And that will be the topic of this first lecture. The second lecture will be focused more on the many-body problem and the challenges that are presented. And there I want to do more guiding principles and not as much details. These lectures are taken from two books that I've worked on, and to the lower left is the second edition of this book, Electronic Structure, which came out last year that Hoon mentioned. And at the right is the book on interacting electrons. The theme in both books is the same. It's that this is a many-body problem, it's a hard problem, and the difference is that in the area of density functional theory has become so useful and so important that it's worth devoting many pages to how it works, and putting off the specifics of the many-body problems and the methods that are used there. So I will not be going into methods, but I will be talking about the general ideas in the next lecture. So the outline for this lecture is, I need to change something here so I can see my slides better. Whoops, that's not what I want. I want to see myself. Oh well. Okay, I'm just moving that picture of myself over to the side. So the outline of the talk is that I would like to start with the development of electronic structure theory from the 1920s and point out how much was done in the early days that we still use today. And the problem of interacting electrons then had the hallmark of the density functional theory in the 1960s, when that was a major turning point in what we could do. More discussion of the exchange correlation functional and some selected examples of the progress of density functional theory. I'm really not going to do much of the examples. I more want to get the concepts and illustrations, and more about the recent advances beyond the original cone-sham approach. So a bit of history. it's almost 100 years ago now that the first ideas of quantum mechanics was from Louis de Broglie, and within 2 years, there was a Schrödinger equation, Pauli exclusion principle, Fermi statistics. Very quickly, the Thomas Fermi approximation, and the first density functional by Dirac in 1928. I want to point that one out because it's in the form of modern functionals. It was the exchange energy of the homogeneous electron gas used as a density functional. Of course, the relativistic quantum mechanics equations of Dirac were done in 1928, and the Bloch theorem in 1928. So the stage was set. And already in the 1920s, there was a many-body calculation by Hilarius that was numerically almost exact calculations for 2 electrons in helium. At the same time was the work of D.R. Hartree, who's carried out numerical solutions for electrons using the approximation that they move in a potential, an effective potential. So they move independently in this potential, and the idea is, of course, that that takes into account in an average way, the interactions between electrons. So this was already done in the 1920s. So the theory for independent particles was well understood, and I want to show this because I want to use the notation later. That here's a Schrödinger's equation, and for non-interacting particles, the ground state is given by filling the lowest states, and the density is just the sum of squares of the eigenfunctions of those states. Of course, the Bloch theorem says that for crystals, the states can be labeled by crystal momentum and a band index, but I want to keep just the simple index that will apply to all cases. Even though everything was known about how to write down the independent particle equations, the major issue was, what is the potential that goes in those equations? For anything more than one particle, it must include some of the average effects of the other particles. And one has to add terms in the total energy that take into account the interactions between the electrons. So the ideas for how to do the independent particle calculations are there. And my next slide is, whoops, I'm doing the wrong thing, is how much was developed in the 1930s and how smart these people were to figure out how to do these problems, taking into account the interactions of the electrons to the extent that they could. So already in 1930 was Hartree-Fock, the Wigner-Seitz and Slater work in the early 30s that did quantitative calculations for sodium, and Slater even proposed the augmented plane wave method that's in a form similar to what's used today. Pseudopotentials in the early 30s were in a form close to what's used today. And I'd like to note that Shockley in 1939 actually realized that there were situations where surface state must occur on the surfaces of covalent crystals. And the way he did it was literally a forerunner of topological insulators. So an important part was the first understanding of semiconductors. And it's a nice story that 2 of the 3 inventors of the transistor in the 1940s were John Bardeen and Bill Shockley, who were both people from our field. Bardeen was a student of Wigner, and his thesis was on the Fermi surface of a metal. Shockley, student of Slater, on the electronic bands of sodium chloride. By the 1950s was when the first calculations were done on electronic computers. And I think the very first was the bands of germanium by Frank Herman. Here's a figure from his paper, And in fact, it turns out that because he didn't have a very good effective potential, and because he could only do certain directions in the brittle zone, this wasn't actually the information that was needed for germanium, but it was a start. And I have an interesting story that I learned from Frank Herman. Before the computers were available at IBM, where Herman worked, Herman's mother did calculations on a calculator. Later, he did the computer calculations, and he said he never found a mistake in his mother's work. So what about the original problem, the problem of the grand challenge of interacting electrons? Why is the problem hard? Well, remember we said that in 1929, already there was a calculation for 2 electrons, which means a 6-dimensional problem for 2 electrons in 3 dimensions. What if we have 3 electrons, or 100, or 10 to the 23rd? The difficulty scales exponentially with the number of electrons, and even the most powerful computers today can't solve the problem just straight brute force. In the chemistry world, there's a lot of efforts that have made very powerful calculations that are scale much better than exponential, but nevertheless, it's still very difficult to treat large systems. And of course, with a solid where you have many, many electrons, then you just have to take a different approach. So the landmark years that were turning point for what one could do with quantitative calculations was 1964 and 65, particularly the work of Hohenberg and Kohn and Sham in setting up density functional theory. But it's also interesting to note that those very years were when the other most widely used methods for quantitative calculations in solids were developed. The GW approximation, which is a many-body perturbation theory, was formulated by Hedin in 1964. And quantum Monte Carlo calculations were done by Bill McMillan, who was a student at Illinois. He was a student of Bardeen. And he did actual calculations on the computers that he built and had in the basement of his home. So this is a method that uses random sampling to treat the many-body system, and it's become the method that's the benchmark for work on both molecules, for large molecules, I should say, and for solids. So here's the Hamiltonian. It's easy to write down in 2 lines or 1 line, and it's hard to do anything with it. I've used the small letters for electrons and capital letters for the nuclei, and the terms in the Hamiltonian are the kinetic energy of the electrons, the interactions of electrons and nuclei, the electron-electron interactions. The only small term is the kinetic energy of the nuclei, which can be ignored and treat the nuclei as classical fixed objects. The one can put back in the kinetic energy later as a perturbation. And if the nuclei are fixed objects, then their interaction is just a number that can be added. And the essential part of the problem is the top line, which is the interacting electron problem and an external potential. So external always means something outside the electron system. And in this case, it's the nuclei, but it could be a potential that involves more than just the nuclei, like applied electric fields, etc. So we'll refer to it as electrons in an external potential. So what did Hohenberg and Kohn do? They did not treat the Hamiltonian directly. They formulated their theory in terms of the energy, the expectation values of the Hamiltonian, and they took the terms that were difficult to deal with, the kinetic energy and the interaction energy between the electrons, and put them together and called it a functional. This Hohenberg cone functional. That contains all the hard parts of the problem. The other part is the interaction with this external potential, and because this external potential acts on just a point at a time, it has this very simple form of just an integral over space of the potential times the density. So let's look at that a little bit more. This is a functional, and it helps us illustrate what a functional means. A functional is a function of a function. And this is an example. In order to evaluate it, you need to know the entire function for the potential, the entire function for the density. But the result for this particular function though is very easy. It's just the integral. The Hohenberg cone functional is another story. It contains things that are very difficult to calculate. Let's look at it. We know that this object can be considered as a functional of the external potential because everything follows if you can solve the Schrodinger's equation that involves the external potential. So it's then a functional of the external potential because it's known in principle if the external potential is known. What Hohenberg cone did was to show that it also can be a functional of the density, that it must be a functional of the density. So before we mention exactly what they did, let's take note of how important this change is. If it's a functional only of the density, then it's a universal thing. The only things here are electron kinetic energy and interactions. So the density itself might be determined by the external potential, but the functional form, the way that this depends upon the density should be universal and the same for all problems. So I'm not going to actually write down what Hohenberg and cone did, but the essence is it's a very simple proof that there's a one-to-one correspondence of the ground state density and the external potential. The demonstration is that if you choose a density, there's only one unique potential, that is except for an arbitrary constant that doesn't matter, for which the ground state density of the system with that potential is equal to your chosen density. So this one-to-one correspondence means that the ground state density determines the potential, and of course the potential determines everything. But that doesn't get you anywhere. So the theorems provide nothing in the way of help for what you actually do, except to say, go back and solve the Schrodinger equation. Was that worth a Nobel Prize? What was worth a Nobel Prize was the ingenious idea of Kohn and Sham to construct an auxiliary system that made a working density functional theory and made it possible to make good approximations. What they did was construct an auxiliary system of non-interacting electrons. This is particles that have the mass of electrons and are fermions, but they don't interact with one another. And then must include functionals that take into account the effects of the interactions on the actual system. And those terms are then broken up in their way of doing it in terms of a Hartree energy that I'll mention on the next slide, plus all the issues that involve the many-body problem, called the exchange and correlation functional. And this is where the Hohenberg-Kohn idea really comes in. It's that the Hohenberg-Kohn theorem says that everything is a function of the density. So this quantity is a function of the density, and it must be universal. And if you consider it as a function of the density, then it makes possible ways to create approximations that are very useful. In principle, the formulation is exact, and in practice, it makes possible useful approximations. So here's the actual formulation. Tony and Sham rewrote the energy in a slightly different form from what Hohenberg and Kohn did. They considered the kinetic energy of independent particles, which is the particles in their auxiliary system, which is easy to evaluate in terms of the wave functions of the auxiliary particles. The external potential, the effect of the external potential is exactly the same because that only depends upon the density. The other terms are broken up into a Hartree term. That means just the Coulomb energy as if the electrons formed just a uniform charge density, and this would be its interaction with itself. And everything else is lumped into this exchange correlation term that includes all the many-body interesting difficult effects. So everything above the green line involves the auxiliary system in a simple way, and it basically leads to a soluble problem. And the difficult parts are put in this exchange correlation term, and we can just say it's not known, it's maybe even unknowable, but the way it's formulated, it leads you to ways to make approximations, and the new paradigm for how to do calculations in condensed matter physics is to find useful approximations for the functionals. So I would say that one of the reasons for its great success is dividing the problem into two parts. One part is finding the approximations, and that means you can test the approximations on test systems and decide what's a good approximation for some large class of materials. And then once you've decided on an approximation, then from that point on, you know that it's a soluble problem. So relatively few people spend their lives in the density functional world of trying to understand what these functionals are, and they're very, very tricky points. And a much, much larger group of people can actually use the functionals and do interesting things with them. So the final equations that I want to show are the Kohn-Sham equations. Kohn-Sham theory is just to get the ground state energy and density. It doesn't give you any direct information on other things. And if you only want the ground state energy, what you need to do is to minimize this energy, the Kohn-Sham expression for the energy. And if you're minimizing it, you also get the density for that minimum energy state. So since the variables in this auxiliary system can be viewed as the set of wave functions for the particles, these equations can be developed by saying that you must get to the stationary point of the energy with respect to all those variations, with the constraint that the functions have to be orthogonal since they're fermions. So, and that immediately leads to the Schrödinger-like Kohn-Sham equation with a potential that's given in terms of the external potential and the terms due to the internal interactions with the other electrons. And the difficult part is the part that's it's not difficult to use once you have an expression, but the interesting many-body parts enter through the exchange correlation functional and its derivative, which is an exchange correlation potential. So in this case, we have a well-defined problem of interacting particles, and we have a way of finding what's the potential that goes there. Remember that these are auxiliary things, so Kohn and Sham warned us not to interpret any of these things literally, but in fact these eigenvalues are rather close to what could use for a band structure, and there's great temptation to consider them as an actual band structure, but we'll say more about this later. So what is the exchange correlation functional? If there were no interactions, you wouldn't need to worry about this. But it's the difficult part of the problem is to include these many-body effects due to interactions. And fortunately, there's a pictorial way that actually helps us understand the exchange correlation energy in the ground state. Near each electron, there's a reduced probability of finding other electrons because of the exclusion principle and because the Coulomb interactions push away the other electrons. So the result is a hole in the electron density, a decrease in the probabilities of other electrons around a given electron. And this is an example for an isotropic system like the homogeneous gas, and a very simple picture of something that's not isotropic. The energy is the integral of the interaction of the electron with this deficiency of other electrons around it, and that depends only on the spherical average. So we have a picture of how you can think of the exchange correlation hole and how it comes into the exchange correlation energy. So how do we actually do something? The one approach is to find a model system that actually, where we know the result for the exchange and correlation, and then use it in the systems that we care about. That was the approach of using the homogeneous electron gas that was suggested in the original paper of Kohn and Sham. The local density approximation is to assume that at each point there's a contribution to the exchange correlation energy that's the same as if an electron was in a homogeneous gas with the density at that point. And since that's known, there were rather accurate calculations even before, but now we have essentially exact results using quantum Monte Carlo for this functional, this is a function of the density. Then once you make that local density approximation, that's it. You can consider it, you're testing the approximation because everything else is in the problem is known. Then there's better improvements that I'd like to take into account that the density of the system you're actually working on is not uniform, including these generalized gradient approximations. And many other developments that we'll come back to later, including hybrid functionals and Van der Waals functionals, etc. So, but I'd like to take a moment to give an idea for how the work with a local density approximation could possibly work in a system like that's very inhomogeneous. This was some work done by Ulla Gunnarsson and his co-workers in the 1970s. They did a calculation, a Hartree-Fock calculation for neon, and in which case you could calculate exactly the exchange hole. We'd love to have the correlation, but that's much more difficult to calculate, and we can get the ideas by looking at the exchange only. So this is what it looks like. We've choose our origin for the for the coordinate system at the place where we'd like to evaluate where we'd like to place an electron to evaluate the exchange correlation hole, and they've chosen one where the nucleus is separated by about 0.1 bores. So the exact hole is basically very large back on near the nucleus, because it's the exchange with the other electrons, and the other electrons are mainly there. On the other hand, if it was a homogeneous gas, it's the same in all directions. Would you think that this dash curve is a good approximation for the solid curve? Well, I think not. But this is where we're saved by the idea that we're looking at the energy, and the energy is a spherical average. If we take the spherical average around the points centered where at this red point, and look at the density, or it's really the decrease in density of other electrons, we find the corresponding curve for the local density approximation and for the exact, which means exact exchange term from Hartree-Fock. And I think you might say that's a good approximation. This gives you some rationale for why the local density approximation, taking something from the homogeneous gas, can actually work in something as inhomogeneous as a neon atom. It also teaches us that what we get from the calculation is not anything to do with the actual correlation in the system. What we have is something that relates to the correlation energy that integrates to the correlation energy in the actual system in order to reproduce the actual system. We're not getting information on the correlation itself. Okay, so there are just thousands and thousands of density functional calculations nowadays, and it's not my purpose to go through them. My purpose is only to show you some typical ones and interesting ones that have had a big effect in our field. One class of problems is where we know the answer very well from the experiment, and they're used to test the functionals. Whereas another class is where we deal with problems that aren't so well known and where the experimentalists don't know the answers. And those are cases where we can make predictions and do direct simulations and provide a lot more understanding than you can get from experiments alone. And this is basically a revolution in the role of how theory works alongside experiments. And work has been done on surfaces, liquids, defects, nanostructures, phase transitions, all with either the same functional for a whole lot of systems or different functionals that can be justified for why one would choose a functional. So it really is doing a lot of work with one or a few functionals. Here's the very first calculation that really put density functional theory on the map. This was in 1977, and it's the lattice constants and the cohesive energies and the bulk modulus of the entire series of the 3D and 4D transition metals. The solid lines connecting the dots are the theoretical calculations, and the crosses are the experimental numbers. And this put DFT on the map because that agreement is just spectacular. And it's actually interesting, the ones where there's a deviation. And these are the atoms that tend to be more magnetic and tend to be more strongly correlated. And it's already a hint from that very first calculation that these are systems that one may have to look at more carefully. Another calculation that had a huge effect was 1982, when Yin and Cohen calculated the energies of silicon in the diamond structure and in metallic structures where the equilibrium constant is where they're dense structures. And this relates to what happens when you put diamond silicon under pressure and it transforms to a metallic system. The fact that you could get the difference in energy between an open covalent structure and a more densely packed metallic structure was really impressive, and showed people that you could do many things with the density functional theory. On the right is an example where there was a utter failure. The local density approximation predicted that quartz would actually occur in a dense structure and nothing like the structure it really occurs in. So that's where improvements, especially with these gradient approximations and then with later approximations, get over some of the bad problems of the local density approximation. And now we have much better agreement and really impressive agreement for many systems. I'd just like to show one example that I particularly like. This is the hydrogen sulfur systems that were the highest temperature superconductors known at the time. I think there are some that are a little higher now, but they are still the basic idea of hydrogen materials under high pressure, and the predictions were, for all of them, were done before the experiments. In the case of hydrogen sulfide, it wasn't even clear what was the compound that was present at high pressures. Because there were many possible hydrogen sulfur compounds, that at low pressure it's H2S, but the calculations show that at high pressure it's H3S, which forms this nice simple crystal structure that's shown at the right. So, and these calculations for the other structures on this diagram show that none of them are stable. They would all decompose to hydrogen or sulfur or the H3S up at the pressures. That's where the high temperature superconductivity actually occurs. The advance that really made things much more possible to treat complex systems was the Coherent advance. They had the brilliant idea of solving the Kohn-Sham equations for electrons and the Newton's equations for the nuclei all at once. And this just opened the doors for a revolution in what could be done. By solving the problems at once, you can relax the systems, define structures. You could do first principles molecular dynamics with calculating electrons as the nuclei move thermally. You can look at chemical reactions as the nuclei move to form bonds, and really a new relation of theory and experiment. In fact, the actual ideas of the way they solve the problem is not used very much anymore, but the ideas they had for how you make the methods efficient are the basis of most of the actual methods done today that have made the calculations so efficient and so applicable to large complex systems. Here's an example of one of the first calculations. Julia Galli was a postdoc with me at Illinois. She had previously worked with Karin Perinello, and she came to Illinois because we had some of the biggest computers that were available anywhere. And we did the biggest calculations that had been done at that time. This is a snapshot of the picture of carbon atoms in molten carbon, showing just the idea of how the atoms move between 2 and 3 and 4-fold coordinated bonding during a simulation. The idea for doing this was that it has relevance for planetary and physics and geophysics, like these conditions that are shown here. But really, we just wanted to tackle an interesting problem. And our first question was, does the melting point of diamond increase or decrease if you put it under pressure? And we found that it increases, unlike silicon, which was opposite to a lot of the predictions that people had made at that time, who would just assume, well, it would be like silicon. Nope, you have to go to very high pressures, and then the melting point starts decreasing, like silicon, and the calculations actually show you why all this happens. Another example that I found really impressive is the study using the Carr-Parnellum electrodynamics method of a very important problem that's very important for industrial production of polyethylene. It's the Ziegler-Natta reaction for adding an ethylene to a polyethylene polymer to add one more ethylene to the length. The intermediate step is a transition state on this catalytic surface, and how the reactions work there was the aim of this study. They could actually carry through the calculation well enough to see the atoms actually moving through this transition state. So there, like I said, there are thousands and thousands of calculations, and I just wanted to pick out something that I found last week. Actually, this was last week, 3 weeks ago, when I actually made this slide. But I was looking at Science magazine trying to understand what is a flow battery, that because it's supposed to be important for possible mass electrochemical energy storage for renewable energy in the future. And it was really nice to see their density functional theory calculations of a series of molecules also suggest that this is the way density functional theory can work with experiments. And almost every issue of Science magazine has someone using density functional theory. It's entered the lexicon of the terms that people are supposed to recognize. If you mention DFT, people in many fields recognize what you mean. So there are many developments of new functionals, and it may be extremely confusing. And I think what John Purdue did in organizing them on a ladder is very beneficial. So this is a ladder, he called it Jacob's ladder, arranged in order of increasing complexity and also in increasing power, starting with the local density and the gradient approximations at the bottom, and then adding other information that's contained in other functionals. So this can be sort of as a generalized cone-sham approach in which you treat the exchange correlation functional as not just the functional of the density, but add information from the wave functions, like the exchange from Hartree-Fock that's included in hybrid functionals. And in the DFT plus U calculation, you're adding an extra interaction U, called U, to the system for selected wave functions. So it's something that depends on the particular wave functions of your system, and it incorporates things that are important. And when you have sort of localized functionals like in the D and F states, you can go on to functionals that involve the polarizability as well as the wave functions themselves. And you might think this could be important, since the polarizability is the response of electrons, and that's exactly what happens in correlation. So here's an example of the improvement using hybrid functionals. This is germanium, and this is the famous band gap problem, and which the germanium is the main example. It turns out to be a metal in local density calculations, zero gap. On the other hand, Hartree-Fock is almost as bad because the gap is so large that it's very, very far from the experiment. The hybrid functionals have been developed to the point where they can reproduce the band structures extremely well. This is comparing information from photo emission and inverse photo emission, and we see that the agreement is really exceedingly good. If we look at the whole classes of materials and consider the improvement in the band gaps, we can look at it this way. This is a plot with each material plotted with its experimental gap, and calculated gaps using various methods plotted vertically for a given material. And if an exact calculation would be if the dot lies on this 45-degree line, which means the calculated and the experimental gaps agree. This shows the basic problem that the local approximation and then also the gradient approximations give gaps that are just much too low. But the hybrid functionals and some improved functionals are really much better and give agreement with experiment that's really quite impressive. There's one more really big thing that's happened in density functional theory that I want to point out, and that's time-dependent density functional theory. This had been used in sort of an ad hoc way before, but it was put on a rigorous basis by Runge and Gross in 1984. It's interesting to note that it really was a current functional theory, and it was turned into a density functional theory using the continuity equation that relates the divergence of a current to the time derivative of the density. So that works very well in molecules and has been very successful. It's very widely applied, and it's one of the biggest uses of the calculations in chemistry, especially for large molecules, and more in physics as well, for problems like molecules on surfaces. That's very interesting for catalysis. It has not been used very much for solids for a very simple reason. The minimum gap has not changed at all. It's interesting to know why, and it's because this continuity problem, the change from the current to the density is something that's really quite non-local, in the sense that the time derivative of a density at a point relates to the current, but the actual pileup of density can be at points that are well, anyway, it's difficult to work this out in the solid, and I'm getting my tongue twisted and not saying it properly. But more recently, there's been worked out how to do it, and we still have this problem that minimum gap has not changed, but we get some very interesting results nevertheless. Here's examples for gallium arsenide and lithium fluoride. This is this same functional that I mentioned before that gave the great improvements in the band structure of germanium, and in the time-dependent using it in the time-dependent theory doesn't change the gap one bit, but it changes the weight in the continuum, and it brings it to more like the experiment. There's a much bigger effect that occurs in a material like lithium fluoride. There, the optical properties are dominated by an exciton, and the local density approximation or some of the functionals like the hybrid functionals like this HSE is designed in such a way that you cannot get an exciton that is bound inside the gap. You can't get a lower energy of excitation than the ones that are defined by the start of the continuum. The way that you get a bound state is only because of the way the response function works out, and it turns out that there's some recent work that has made it very possible to use the standard machinery nowadays with hybrid functionals, but only if they contain some long-range terms in the hybrid functionals to do straightforward calculations that include things like the excitons and solids. I'd like to point out that there was some early work that showed the direction for this by Young Kim and Andreas Gerling in the 2002, and by other people too, of course. And but now it's become something that's much more useful, and people know how to fold it in with the other ways that they're doing calculations with density functionals. So my conclusions for this lecture are the cone-sham density functional theory has revolutionized what we do with the theory of condensed matter. The key to this success was that the problem was divided into two parts. Finding the functionals, which is a big job, but using the functionals, which opens just all kinds of opportunities and possibilities for studying materials. And because it's so useful, there are these codes that have been developed that are very, very useful. The challenge is then to solve interesting problems. So I'm going to stop now, and in the next lecture, I'm going to talk about some of the major challenges due to the interacting many-body problem and some guidelines for how to look at this. So thank you.
Thank you, Richard.
Okay.
Yeah, let's take some questions if there are any.
I'd be delighted.
Okay, so 질문 있으시면은 혹시 지금 뭐 채팅을 하시다거나 아니면은.
Okay, I'm going to stop sharing now.
Yeah.
And I hope to be able to see you. Okay.
Okay, do you? Okay, so now you can see us. 자, 질문 있으시면은 그 문자로 남겨주시거나 아니면은 거기 마이크를 켜시고 얘기를 하셔도 되는 걸로 알고 있는데요.
Can I ask a question?
예, 질문하십시오.
Okay. Thank you very much for very pedagogical lecture. I'm actually outside of density functional theory, so please forgive me if my question is too stupid. Anyway.
방 소장님께서 먼저 소개 좀 잠깐 시켜드릴까요? Richard. So Professor Bang is the chair of the APCTP. So he was here. I didn't know. Okay, please go ahead. Yeah.
Yeah. Let me disclose my face. Nice to meet you, and thank you very much.
Yes, good.
Yeah, as I said, I am outside of this density functional theory, and you also mentioned at the beginning of your lecture, and I also heard many times that everything depends on just the density. So if you find the correct density, then you can find everything exactly. So this density function, right?
And that's just in principle statement, yes.
And you said this is proven mathematically.
Yes.
Yeah, I believe so, but intuitively, still I have some question, because when we solve this quantum mechanical problem, we eventually find out wave function rather than density.
Yes.
So my stupid question is that if you find just the density and you can determine everything exactly, that means, is there any redundant information in wave function?
No.
So that's number one question. So number two question is, nowadays the topological material is very important. So topology means you need to know the information of wave functions. So then how can you compromise or anyway, you understand my question.
I think so. And that's a wonderful question because it really makes us think, what does all this mean? And the people in density functional theory get tied up with all the nuances of what's a functional of what.
Right.
So I wanted to make these big statements because it's sort of the simple way to see things, and because it is what led to the abilities to make good approximations. But remember what I really said was that idea that the density determines everything is really a very hollow statement. That all Hohenberg and Cohn proved was that the density was enough to determine the external potential.
Right.
And then I'm sure you would agree that if you know the potential, then in principle you can get the wave functions. So it's not saying that in any simple way you can get the properties of the system just from the density.
Question. So when you say, if I know the potential, of course, I know I can solve Schrödinger equation exactly. But here, when you say potential consists of external potential together with the other electrons, the potential provided by other electrons. So do you mean the potential consists of total potential or external potential?
I mean, it's external potential. And the idea is that all those electron-electron interactions are internal, and they're part of the big problem that's so hard to solve.
Yeah.
So let me then follow this up with what I would have loved to have done, and I do in some lectures, that why was it so helpful to identify things as a functional of the density?
Right.
So finally, in the end, the only thing that matters in the Cohn-Sham approach is this exchange correlation energy,
right,
and how it depends upon the density. And think about it. If you were to try to imagine how you would calculate the correlation of a particle with all of the other particles, the first thing that comes to mind is the density. How close are the other particles to you?
Right.
So because you're formulating it in terms of the density, it's what actually makes it so helpful in making approximations. And then that's really what's done in practice in real density functional theory.
Then can you answer to my second question? Can you find out topological property just using density?
So now there we are. It's once again, it's the same issue of how it's sort of turned inside out. Remember that the auxiliary system actually has wave functions. They're very simple, but they're wave functions there. And in my second talk, I'm going to talk about the basic idea of how you can get the topology of the real interacting electron system, starting from those wave functions, like the Cohn-Sham wave functions.
Okay.
So it's an interesting. I won't answer this question in depth. I will say we can understand how it's possible to do it.
All right. Thank you very much.
Thank you for questions.
Richard, so you might want to take some break before beginning the second lecture.
I'd love a little break, but it doesn't have to be long. It's whatever suits you.
Okay, so if you see the chat window, there are several questions. So,
okay.
Yeah, you might want to come back in about 5 minutes after break, and maybe if it's okay with you, then you can make some comments on these questions.
Okay, if I can do it by speaking, I will really be happy because I can't type very fast.
Yeah, so, but then you can do it after the break, 5-minute break.
Okay.
Maybe, yeah, so.
Okay.
So, yeah, so 5분 정도 쉬었다가 지금 저희가 약간 스케줄이 늦었으니까요. 그 5분 정도 쉬었다가 이제 그 질문 더 들어오신 거 잠깐 받으시고 그 다음에 두 번째 강의 시작하시는 걸로 하겠습니다. Okay, so maybe you might want to take some rest and then begin again in about 5 minutes. Then,
Okay, so 5 minutes from now.
yeah. So
Okay, and I'll look at the some of the chat, but I'll see if indeed I'm able to actually do anything useful. So, but I'll look at it during this 5 minutes.
okay, so maybe you,
Okay.
you might want to get some stretching or get some water or some things like that.
Okay.
So, yeah. So
Very good.
whenever you are ready, then let's get started. Yeah.
Okay, excellent.
박세영 교수님을 채팅으로 다 문제를 박세영 교수님 손을 들었는데
근데 우리
예, 채팅으로 질문하도록 하겠습니다. 네.
예 채팅으로 해주세요 채팅
예, 예.
예. 채팅 올려주시면 나중에 질문 답을 하시고 아마 이제 두 번째 강의 시작하시면 될 것 같습니다.
Hello, Young Hoon.
Okay, Richard. So, should we start the second lecture then?
Oh, I'm ready when you are.
Okay, so I mean you have to go to bed soon, so let's get
Oh, no,
started.
that's all right. Oh, this is not late.
Okay,
So I can make some comments on the chat, but only little comments, if that would be useful.
if you feel it might be better to answer the question at the end, I mean you can maybe skip also. So
Okay,
feel free
okay,
to do
then,
so, yeah, as you wish. Yeah.
okay. So then I'll wait and do that later.
Yeah. Okay. Maybe it might be better that you do the second lecture, and maybe then they will understand a bit better at the end. Yeah.
Okay. Okay. Do you want me to start?
Yeah. Then please get started. Yeah.
Oh, okay. Okay. Then I'll try to share the screen.
자, 그러면 그 질문은 한꺼번에 몰아서 두 번째 강의 끝나고 받는 걸로 하시겠습니다. 예. 두 번째 강의가 약간 거의 스트롱 리코이트 시스템과 관련돼 있기 때문에 지금 나온 질문하고 약간 연관이 될 것 같거든요. 예, 그럼 두 번째 lecture 시작하도록 하겠습니다. Okay, please.
Oh, so good afternoon again. I hope you're not too tired of hearing me talk. The second lecture, I would like to do something that maybe is a little surprising for this kind of a start to a school. This is one could say much more about density functional theory and things that are more practical, but I think the thing I can contribute best is some pictures of how one thinks about some of the problems that may be very complicated. So what I'm looking for are guiding principles. Almost always in difficult problems, one has to make approximations and assumptions. And certainly electronic structure is one of these. You have to make approximations for what kind of functionals you use. Other methods like GW and DMFT have approximations like in which set of diagrams you sum in the many-body perturbation theory. Except for very small systems and wave function methods, you need to consider only a small number of the possible excitations of the system for that in a large system that cause the exponential growth of the exact solution. You often have numerical approximations. Maybe more important is that you may have assumptions of symmetries and order, and that may be very important. And it's another thing. Temperature is often important in the actual properties that we care about, but often we don't do anything about it in the calculations. And so guiding principles for what happens as a function of temperature. And the big question is, how can we be confident in drawing conclusions from calculations on a very difficult problem? So this is guiding principles with pictures and no equations. So by the end of this lecture, I hope you can appreciate how you might say, you will find your own problems to deal with, of course, but the example I'm going to use is, I'm a person who's been working on a hard problem. I realize my calculation may be off by a factor of 100 or 1,000, but I can confidently draw certain conclusions because of conservation laws. And the factor of 100 or 1,000 is interesting. It may indicate new challenges and interesting new possibilities. So the guiding principles I want to talk about are continuity and conservation laws, order and symmetry, things that have to do with temperature and disorder. And want to use both models, which are very instructive for bringing out concepts and phenomena, and and materials that provide outstanding examples of the effects. The ideas are in this book on interacting electrons, and the guiding principles are attempted to be buried throughout the book and mentioned quite specifically in the introduction. So let's do something on a moderately correlated system just to get started. Here's a question. In a textbook, you find pictures of independent particle bands like silicon. Now, let's ask ourselves, is this just an independent particle problem? Or does it really apply to the real many-body interacting problem? We may have used independent particles or some other approximations to get the actual values for the band gap, but the gap itself is not an independent particle concept. The lowest energy for adding an electron and minus the lowest energy for removing an electron is the gap. And since you're the lowest energy for any of the possible things that can happen to the electrons, there's nothing lower that they can go to. This is something that's really well defined in a many-body sense. If you go far away from the band gap, you're considering states that might decay to other kind of states. So they may not be, and they aren't so well defined. But some things we can say are really well defined. And the only question is how accurate are our calculations. You might think this was rather trivial for silicon, but in fact the questions become not so trivial when you get to complicated systems. Let me just mention something. Topological systems was asked about in one of the questions after my first lecture. That involves the states at the at the edge of the top of the occupied states and the bottom of the unoccupied states, and when they switch is a topological transition, is something that then it becomes a well-defined concept, even in the many-body picture, even though you might think of it in independent particle pictures. So let's look at another case. The case that was mentioned before, germanium, and where the hybrid functionals seem to work very well. So I forgot to say, this idea of moderately correlated, I think a general way of saying it would be places where perturbation approaches work well. And so this is a case where that should be true. And here's an example of work using the GW, that's the many-body perturbation method for calculating the bands in germanium. And it's compared the same way that the ones above are. This is this terrible local density result and the Hartree-Fock with a very wide band gap and the many-body calculation in the middle. You might say that these look almost identical. And that's not just an accident. The hybrid functional involves the part Hartree-Fock, and it's been adjusted. It's been tuned in such a way that it's pretty good. The many-body perturbation method is in fact set up, and the way that diagrams are chosen in this GW approximation can be viewed as screened Hartree-Fock. So they actually have a close relationship, and the many-body calculations can be used to justify and to derive new functionals. So it's a good relationship with density functional theory. So what about more strongly correlated systems like Mud Insulators, heavy fermions, the high TC materials? What are the symptoms that cause someone to say that a material is highly correlated? What usually happens is there's some signature, And for example, a phase transition or an order like magnetism. In fact, we know that magnetism can occur only if there's interactions. But then there's a question whether, now does that necessarily mean that they're strongly correlated or not? In general, these strongly correlated systems, so-called, have large effects of temperature because they have low energy scale, and they're very, you can change between one state and another with little energy, which is why they're so interesting and useful. And there are other cases where they're really extreme phenomena, like systems that act like they have effective masses 1,000 times more than others. So what materials do this? If we look at the periodic table, the systems that have D and F states in this transition series are ones where there's these rather localized D and F states that are somewhat atomic-like, and in the lanthanides, they're like very atomic-like, even though they're in a solid, and they're in conjunction with other more band-like states. So these more localized states are ones where the interactions tend to be larger, and they're the ones that tend to give this more strong correlation. This can be seen in another way. This is rearranging the rows of these transition systems from the most localized, the 4Fs, to the most delocalized, the 5D. And as you go across the table, things get more localized because the nuclear charge gets larger and the states are pulled in more toward the nucleus. So in the upper right are systems that are very localized and magnetic, and they're basically described by spin models. At the lower left is systems that are basically described by band models, and one of the features that often happens is they're superconducting, and it's just places in the middle that are between the superconductors and the magnetic materials, so the ones that have the most anomalous properties. This includes cerium, for example, and uranium. The materials like nickel oxide that we'll mention later falls in that category because as an oxide, it pulls the oxidation state over into this most interesting range. Similarly for the copper oxides and the high temperature superconductors are actually in this interesting range. So let's get some models that are useful and instructive. Probably the most widely used model is the Hubbard model, which corresponds to having a lattice, and on each lattice site you have a system that has two states, an up and a down state for the electrons, and if there are two electrons on site, there's an interaction U. And if we look at the half-fill case, we can look at the spectra. Now, this is not the spectra of any particular crystal. If there's no interaction, this is called the semicircular density of states, which makes a marvelous problem because you can actually work out things analytically. And as you turn on the Coulomb interactions, the first thing to say is there are no exact solutions, period, for this problem or for any lattice. So we're now working with approximations, and we need to justify and see what we learn from them. So Hubbard made one of the ways of thinking about this problem based on the fact that if you have large interactions, you expect a large energy scale. And if the interactions are large enough, you'd expect to find that it would be very difficult to put two electrons on a site, so it would be a very high energy compared to taking an electron out, which would be at very low energy. So the difference would be basically this Coulomb interaction. So you basically know that has to happen. By the way, I didn't say this quite clearly enough. This is a half-fill symmetric problem, so everything is just defined to be symmetric. So the energies the Fermi levels is fixed so that it's exactly in the middle between pulling particles out and putting particles in. So you just know that this has to happen in some basic sense. There's another thing that you know has to happen. Gutzwiller realized that the bands get narrower because of interactions. That is, it's harder for the electrons to move from one site to the next. He made an approximation saying, well, let's suppose the system stays as a band and gets narrower and narrower. So what really happens there are two solutions from these two giants in our field is things that you can work on analytically, that the Hubbard model is where at some point you open up a gap and it would look like an insulating state. The Gutzwiller solution is the bands get narrower and narrower until they get infinitely narrow and disappear in a sense. And so let's look at another model. The Anderson impurity model is a model for the Kondo effect, which is in a different category. Because the interactions are only on one site, you can actually do the exact calculations. And so for the model, they're exact analytic calculations. And for more realistic systems, there's ways to do the calculations numerically. So we really know what the results are in this case. So the model consists of a site with Coulomb interactions embedded in a medium that's metallic and is defined not to have any interactions. It's just an independent particle system. The spectrum for this is something that you can understand, even though it's a very complicated problem to work out exactly. You can understand the points. If there's no interaction, it's basically a resonance at the Fermi energy, and it's been defined to be half filled. So that's why it's symmetric about the Fermi energy. If you go to large U, large interactions, we can first look at the Hartree-Fock calculations. There's two kinds of Hartree-Fock. One is restricted, where you could restrict the system to have equal numbers of up and down spins, and that would give a state, right in the middle. But if it's unrestricted Hartree-Fock, it's for large interactions, it's lower energy to say the state has an up electron and it costs energy to put in a down electron. Exactly the same thing happens with the local spin density approximation, or the local spin density approximation plus U. So this would be examples of calculations like that. It could be either Hartree-Fock or in the density functional world, where you have a broken symmetry. Phil Anderson was a smart person, as you no doubt know, and he used this as a signature for when something interesting happens. He knew this wasn't really the full result, but it's when you get the split density of states, it's when it signifies that something interesting is going to happen. And the final exact solution has these Hubbard sidebands that's split by an energy of order U, and it leaves over a very narrow band. Really, it's very narrow if U is very large, right at the Fermi energy, sort of like the Gutzwiller proposal. So it has three peaks. It has the whole picture, and this is now an exact solution. You can understand it not merely by just swallowing what somebody else said. You can understand it in two ways. One is that despite the fact that you got this broken symmetry solution, you know that it's degenerate. You could have had a down spin electron just as well as an up. And it's that degeneracy that couples with the surrounding metal that makes a strongly coupled problem. That's this famous Kondo problem, and leads to the Kondo effect and this feature at the Fermi energy. There's another way of saying it that's basically one of these continuity arguments that I'll use a little later. The Friedel sum rules says that the scattering probabilities for an impurity in a metal are depend only on the amount of charge that's collected. And so that's one of these sum rules that says there has to be scattering that at zero temperature that continues with exactly the same value, no matter how large the interactions are. There's a sum rule that we can say, I really believe, and I believe that requires that peak must be there. So that's the kind of logic I'm going to use later. So here's the kind of thing I would like to learn from this. We have exact solutions. We know it has this Hubbard sidebands kind of picture. We know that for low temperatures, there's a narrow peak that must emerge. It comes from the calculations and it comes from reasoning. And furthermore, at higher temperatures, this gets washed out. If the temperature is larger than the width of this peak, then it basically gets washed out, and it just acts like a spin that's weakly coupled to the bands. I'm going to give you one more thing that may sound terribly complicated, and it is to actually use it in detail. But in fact, it's actually very useful to know that this approach is something that you can understand the basic ideas for very straightforwardly. Dynamical mean field theory is to consider a site that's embedded in a continuum, rather a medium that's a non-interacting system, but very much like that Kondo problem. And if you just treat this as a surrounding medium and an impurity problem, then it's actually the way you could solve the real Kondo impurity problems. And to actually do it, you have to apply the heavy machinery of taking into account the many-body interactions. But to see the general effect, it's just a matter of solving for an impurity in a surrounding host. Dynamical mean field theory is to adjust the surrounding host atoms so that they have the same spectra as the one calculated for the inside atom. That means it's a self-consistent problem to make the thing that you calculate on the central atom equivalent to what's the atoms on the outside. This is just exactly the same thing that's done in Weiss mean field theory for magnetic systems, for how you treat how you make the Weiss mean field approximation. And you may have done this as a homework in undergraduate physics class to understand the thermodynamics of a magnetic system. And it's just exactly the same problem, except it's more complicated. It has but it has the same roots. It's actually the same idea is used for alloys as well, for what's called the coherent potential approximation. So this is a way that you can describe both atomic-like and band-like features. You can describe this Kondo-like problem. You can treat still approximately, because there's no exact solutions for the real lattice problem, but you can make this dynamical mean field theory approach to the lattice problem. You can treat thermal fluctuations. And probably most important for the present talk is that you don't have to treat idealized models like the Hubbard model or the Anderson lattice, which I'll mention later. You can treat realistic models with full parameters from a density functional calculation so that you're doing realistic problems. Okay, now that I've said all that, let's look for some guiding principles that we can apply to those problems and to the real materials problems that I want to address. So returning to the guiding principles, let's look first at continuity and conservation. This is probably the most important guiding principles that I know of. And the principle of continuity was expressed eloquently by Landau in Fermi liquid theory. And the idea was that an interacting system would be connected continuously to an independent particle system where you know exactly what's going on. And a way to think about it is increasing the interactions from the independent particle system to get to the real problem, and saying that the properties evolve continuously. You may change things quantitatively, even by a lot quantitatively, but qualitatively it would have the same overall structure. And the problem he applied it to was liquid helium-3, which is a Fermi liquid that's indeed very highly correlated. I heard from Alexei Abrikosov, who worked with Landau, that Landau arrived at this proposal by asking himself, what is conserved? If indeed there are fundamental requirements that something that's conserved, it does not change as you turn on the interactions, then the system should evolve continuously as the interactions are turned on. An example that he described was if you consider the conservation of momentum. If you have interactions between particles, then the momentum may be shared between many particles, but the total momentum is still conserved. That is, unless there's a phase transition, unless something changes when you turn on the interactions. And of course, Landau was very familiar with that since he's one of the main people that taught us how to classify materials by their symmetry. So the guiding principles that come out of this are continuity and what is conserved in the evolution. Now, discontinuity is not a failure, it just indicates that something's happening. So the most important consequence of continuity that I know of for the electronic structure problems is the Latency Theorem. This is a powerful example of using continuity and conservation laws, and it states that the volume enclosed by the Fermi surface in a crystal is conserved. That is, it's the same in the interacting system as in an independent particle system with the same number of electrons and the same symmetry. This is derived by summing all diagrams in a many-body perturbation theory, and it's valid only strictly at zero temperature. So if you're actually going to write it down, you have it's not so difficult, but you have to define a bunch of Green's functions and carefully label what's happening as temperature goes to zero. But we can appreciate the general properties and how important this can be. Let's be sure we understand this is not a theorem in the mathematical sense. Rather, it is a conclusion that if the expressions converge, or more generally, if there's no change in symmetry, then the volume should be conserved, must be conserved. And if there is some change of symmetry or some divergence, then of course it may not be conserved, and that indicates something interesting. So now let's consider the Mod Insulator. The Hubbard model was an example, but it's much more general. The original example was actually pointed out by Mott in the 1930s of nickel oxide. And in 1949, Mott made the observation and explained it well of why we expect any system of atoms with large interactions, much larger than the bandwidth, to be an insulator. That's just simply because it costs too much energy for an electron to move from one atom to the next, because it has to pay this large price of the repulsive interaction. And this would apply even if there's an odd number of electrons per cell. So the simple reasoning says that any system that has large enough interactions must become an insulator. And that might appear to violate the Latency Theorem, right? Does it? Well, look closely. The electrons has a spin. And most, and maybe all, so-called Mod Insulators have some underlying order, such as antiferromagnetism at low temperature. The order doubles the unit cell or gives larger unit cells. And of course, if now there are 2 electrons per cell, there's no problem in the system being an insulator. And there's no problem with the Latency Theorem because there was a change where it just doesn't apply. Or put it more correctly, you can apply it in a new way to the new system, but it doesn't apply continuously across the phase transition. It's not a violation, it's an interesting phenomenon. So let's see how that works. And now relates to some actual density functional calculations for the Mud Insulator nickel oxide, which orders antiferromagnetically at a temperature less than a nail temperature. And what's shown here is a diagram that has the experiment at the top and a good many density functionals and a many-body calculation using the GW method here and some the other many-body calculations in these panels. So let's start with the upper panel. This is the experimental measurements of photoemission that's taking electrons out of the sample, and inverse photoemission, that's where you shoot electrons in. And the difference for the age is the band gap. And this experiments are done below the nail temperature, but in fact, they don't change so much. When you go through the melting point and you lose the order, it still acts like an insulator. The picture that's shown here is mainly due to the nickel. The matrix elements are such that the oxygens are not observed as much. But then of course in the theory, and then we have other information from other sources of the relative positions of the nickel and the oxygen energies in their spectra. So now let's see what happens if you do the good old LDA calculations. You get the usual disaster. The gap is almost zero, and it's essentially a metal. And the nickel, which is shown with the white area, the oxygen, which is shown with the dark area, are entirely wrong. We know from many experiments that there's a lot of oxygen weight up near the Fermi energy, and the nickel weight is spread way down, way away from the Fermi energy. So this is just basically wrong, and it was misleading for many years. If you do better density functionals, like with adding an interaction you improve the results in both ways. The gap and the way the spectrum is organized. And if you use this functional, the same one that was used for many other problems, it's actually reproduces the results really quite well. The many-body calculation using the GW approximation also is very good. It appears to be even a little worse here, but that has to do with a lot of details. Interesting sounds. So what lessons are we to draw? The lesson that I draw is that nickel oxide is really not so different from all the other materials when it's in its ordered state. So as an antiferromagnetic insulator, the density functional theory works for it about as well as for the other materials on this plot. It may be exceptional in how bad the local density approximation is, but when you use the better functionals, it's the same general quality as for other materials. But what about the disordered state? Now we don't have order anymore. And in fact, that's what these calculations using this dynamical mean field theory were done for. It's actually easier to do them at high temperatures. And so that gives a pretty good picture that the gap doesn't go away at high temperatures. It's just that the system is disordered thermally. So does that mean that the LDA fails? It really does not mean that. What it means is that all this work in the lower parts of the figures that was using the various functionals was a zero temperature problem or zero temperature calculation. We need a method that takes into account the actual thermal disorder in order to properly take into account the disordered system. And so how does one do that with density functional theory? Well, as a matter of fact, this dynamical mean field calculation is just exactly that. It is the generalization of the density functional approximation to be able to take into account the thermal and also the quantum fluctuations in the system. So remember that from that previous slide for what dynamical mean field theory is? It's a theory for a site embedded in the medium and done self-consistently. If you take the parameters from density functional theory, including the U, then in fact this is doing the calculation that it treats the interaction more properly, and it treats it in the situations when the system is disordered thermally. So there's a real sense in which this is the step that generalizes DFT to finite temperature. And the result finally is what was on the previous slide, that the density of states still acts as if it's an insulator, which agrees with the experiment. So now let's return to this question. What is a Mud Insulator? So we've seen that we can explain the case with this antiferromagnetic order that causes the system to turn into an insulator, and it doesn't violate any principles. Other cases would be that phase transition that comes when you have a lattice distortion and opens a gap. So there's a big question. Are there any examples of a Mud insulator that does not have any order at t equals 0? Be like a system with an odd number of electrons that becomes an insulator without doing anything else. I've been asking that question for more than 40 years, and I think the answer still is there isn't a single example, except possibly some very, very special lattices for which a system becomes an insulator without any other order occurring. And it's good to keep asking the questions because because if it occurs, it will be interesting. And in fact, some speculations have been coming around recently that might be very interesting. Topological order. There's a possibility of a quantum order or topological order that would be a complex order parameter that's not something you see with X-rays. It's something that would be the topological properties of the system. And proposals like that have been made by Xiaojin Wen and Subir Sachdev and other people. So speaking of topological insulators, I'd like to mention how this fits into the picture that we're just describing. Probably the best example of all of a conservation law is topology. Topological insulators are one of the most exciting areas of condensed matter theory for the last decade. There's the seminal work understanding them was started in the 1980s, but remember that I pointed out a forerunner by Shapley in 1939 that actually contains many of the ideas of types of topological insulators that people talk about nowadays. All, or almost all, the theory is given in terms of the topology of bands, independent particle bands. So how do we know that the results actually apply to real interacting electron systems? Like, for example, samarium hexaboride. Before topological insulators came along, it was well known that this was a highly correlated material and was sometimes called a condo insulator. It has a very small gap, and that comes about because of the hybridization of some very localized F electrons with the D band electrons. And it's one of the most studied topological insulators because it has some very nice properties. But how in the world could you expect that the theory that involves independent electrons could actually be applied to the samarium hexaboride? Well, the point is just what we've been saying: continuity and something that's conserved. The topology cannot change. For the topology of the electronic system cannot change unless there's a gap that vanishes. So we have a very clear case that if we turn on interactions and there's no gap that vanishes, then the topology of the electronic system will remain the same as in the independent particle problem. Now, there might be some new things that happen, but that would be just some of the interesting possibilities for additional things. But as long as we can be clear that there's no gap that closes, then we're perfectly permitted to use the theory for independent particles to attempt to understand these strongly correlated systems. Now I'd like to in the last item to discuss something that happens in systems that don't have a phase transition. So suppose we have a system that we know is strongly correlated, and it doesn't order as you go down in temperature. What happens? Here's some examples of that involve cerium and uranium that have these very localized F electrons. And we know that they don't have magnetic order or other order down to some low temperature. They may have other order, like they become interesting superconductors at even lower temperature. But at a range where we can actually look at the specific heat and investigate the bands, they act like there's no phase transitions, and they act like systems that have masses that are 100 or 1,000 times larger than ordinary systems that's measured directly in the specific heat, which implies bands that are 100 or 1,000 times narrower than in a typical band calculation. So let's look at an example. Oh no, first I want to go back to the model picture to see what we think must happen. Here is this picture of the condo effect for an impurity, and we already have the picture that at very low temperatures this impurity hybridizes with the medium very strongly, and it creates something very narrow, highly correlated effect right at the Fermi energy. And we also have the picture that if you go up in temperature, this washes out, because if you get to temperatures larger than this kind of bandwidth, the coupling to this medium vanishes, and it becomes basically just like spins that are weakly coupled to the surrounding metal. Well, that already gives us a picture of what would happen if you make an entire lattice of these states, not just an impurity, but an entire lattice. We don't have exact solutions now for the lattice problem, but we can think about how this must work. For high temperature above some characteristic temperature, that's something like this Kondo temperature, we certainly expect that we will just have disordered spins, and they will each act like isolated impurities that hardly know about each other. But if we go down to low enough temperature, then the electrons on these the sites of the lattice will start interacting with each other, and they will do something. They'll either form a magnetic order, or if they don't form order, then they will necessarily produce some kind of a very narrow band. So let's look at an example. This is cerium, iridium, indium-5. Now that may sound horrible to deal with, but in fact, the interesting things are happening on the cerium, and the other elements are providing the background bands and keeping the ceriums far enough apart that they don't interact too strongly with one another. At high temperatures, like room temperature in this case, this is theoretical calculations, by the way. It's backed up with relations to experiment, but the theoretical calculations show it much more clearly. And so this is one of these dynamical mean field theory calculations with parameters taken from density functional. And the result is that at this temperature, near the Fermi energy, the bands look just like density functional bands. There's essentially no effect of the presence of the electrons. Oh, I should say they look like density functional bands if you throw out the F states, if you don't have any F states. So just due to the other states in the crystal. So it's like the Fs aren't there. On the other hand, if you go down to low temperature, you see developing some sharp features near the Fermi energy. And note the energy scale. This is magnified by a factor of 100. So something that you barely could even see on this scale is the interesting bands on this very narrow scale. That may seem like it's something that's hard to believe, but in fact, it's just exactly what you expect, because you know something about cerium in these systems, and you know that this is one of these cases that has these very high effective masses. So this must be a narrow band there. And furthermore, you have a continuity principle, a conservation law, the Latency Theorem, and you're essentially guaranteed that unless there's some kind of a phase transition, that at low enough temperature, you will find this narrow band, and that it will have a Fermi surface that counts the F electrons just as well as all the other electrons. And that's what comes out of this calculation. And that's what must come out, and must be the physics of the real material. So I'm going to stop. We've outlined a few of the challenging problems and the way that density functional calculations might relate to them. But what I'm hoping that you would be able to say for yourself in using guiding principles would be one of the following. I'm dealing with a hard problem, and I honestly do not understand what's happening. I need to learn. Or, whoops, I did the wrong thing. Sorry, I clicked the wrong button there. Or, I'm dealing with a hard problem. I realize my calculations may be off by a factor of 100 or 1,000, but I can confidently draw certain conclusions because of conservation laws. And because I find this big difference of 100 or 1,000, it shows that there's something interesting. It may indicate that there's some new challenging and interesting new possibilities. So thank you.
Thank you, Richard.
Okay. Okay, I will leave this slide up for a moment
Okay, so
because I like it.
yeah, maybe we can get started with the questions then from the first session. So yeah, there were questions about the current density functional and time dependent density functional. The validity of these equations, the formalisms.
Oh, wait, excuse me. And now I'm confused. Which, is this a question in the chat? Or a question
Yes,
from someone?
yeah, on the chat side.
Yes,
Yeah, you probably have seen the questions already.
I've seen some of the questions, yes.
Yeah. So would you like to make some comments out of these questions?
Okay, well, one question was DFT is used for the luminescent phenomena in quantum dots. In fact, it is useful, and this is one of the places that time-dependent DFT has been very successful in predicting the properties of these quantum dots. And so there's a good bit of work. I could give you references for it, but one example is the work of Jim Chelikowski in Texas, and another one is Igor Vasilyev, who worked with Chelikowski, but now is in New Mexico. There's another one that's about machine learning. This is really an interesting possibility, and I know people are working on it, and in sort of two ways: to use machine learning to figure out which functionals actually describe materials best, by using big materials databases. That's something I think I can understand in general, but it's even more interesting if you can find a way to more theoretically find functionals that represent correlation better. So I think that could be a real possibility to use things that we know from many-body calculations and analyze them with the artificial intelligence kind of a way to produce functionals. That would be quite exciting, but I don't know what's going on myself. So this is about these auxiliary quantities that oh yes, does TDDFT work in the same way? No, there are some ways in which it is the same problem, but in fact, it is a proper theory of excitations. So it's not the just pulling these eigenvalues out and using them as meaningful quantities. It's meaningful in the same sense that their static density functional theory is meaningful for the static quantities. These are real meaningful excitations, and it would include optical excitations where you don't change the number of electrons, but you change the density when you make an excitation, and that's fundamentally the reason that it's so useful and used so much in the chemistry world. And there really is a solid theoretical foundation for it, and it's not just arbitrarily using these artificial quantities, or rather I should say auxiliary quantities. I think I may have misled you because I went so quick on current functionals. There's a lot of work in the area of current functionals that's particularly important when you have magnetic fields. And I should have said that from the very beginning. It would have been like line number 1 on the formulation of density functional theory, that we're assuming there are no magnetic fields in the formulation of density functional theory. And that's built in at the point where we say the external potentials are just local potentials that act on electrons at a point. If you put in the magnetic fields where you have currents and you break the time reversal symmetry, then many of the theorems just don't work. That also causes problems in the place where I referred to it in the time-dependent density functional theory, but they are really only meant as essentially the polarization current that's induced when you form an excitation in the system, and that is the way that Röntgen and Gross formulated their theorems. So it's not the circulating currents of a magnetic system that I meant by those comments.
Okay, thank you very much. So I guess you answered the 4 questions from the first session. So let's take some more questions, maybe about your second lectures. 자, 그럼 질문 있으시면은 이제 두 번째 특히 그 강의에 대해서 질문 있으시면은 질문해 주시면은 좋겠습니다. So maybe then I can ask some questions about your second lectures. So you raised the interesting question about the validity of the DFT in view of the strongly correlated systems. So they might be also related with the time-dependent DFT and current dense functionals related questions from the chat sessions. So I didn't quite understand at the end. So do you believe that DFT is capable of treating all these correlated systems in the end, or